Okay, in the previous video we found that the pressure was equal to the force divided by the area, and that could be written as 1/3 of N over V, right? The number density times the mass of the molecule times the root mean square speed square, right? And this is basically the average speed of the particle. So now, remember that if we have a particle moving, right? If we have a particle moving with velocity v, then it has an energy which is 1/2 mv squared. This is the translational kinetic energy. Translational kinetic energy. And that is all the energy of this system if we have just one particle with this much energy. If we have many particles, then we are interested in the average energy. The average energy, and the average energy is equal to what? Well, it's equal to 1/2 m then v squared average. And this is nothing else but 1/2 m v RMS average square. So this is the average energy of the system, right? Of one particle in a gas, not of the system, just one particle. So now let's do a trick here. So we have this quantity here, so we can write P. We can rewrite this expression here as 2/3 of N over V. And then I'm going to write here 1/2, and this 1/2 cancels with this 2, so I haven't done much. MV RMS square, right? So all I've done here is I added a 2 here and a 1/2 here. So now this quantity here, this is E average. So I can write that P is 2/3 N over V E average. So therefore I'm relating the the pressure with the average energy of the particles. And I can go even further and I can write that PV is equal to 2/3, right? N E average, right? So I just send this V multiplying to the P. Now remember the ideal gas expression, PV is equal to N kVT. So all these two PVs are equal, so I get that 2/3 N E average have to be equal to N kVT. So what this tells me is that if I cancel these n's, is that E average is equal to 3/2 kVt. So basically this is telling me that the average energy of each molecule is related to the temperature, or remember, this is basically the kinetic energy. This tells you how fast the particle is moving, and that is related to the temperature of the particle. So this is the main expression here that relates the temperature to the particle. So this is the connection with the connection between the microscopic world and the macroscopic world. So this thing we call temperature measures basically the average translational kinetic energy of the molecules in a gas. It tells you how fast the particles are moving. A higher temperature, all it means is that, well, the particles are moving faster, that this E average is higher. What is absolute zero? Remember that absolute zero? Well, the particles are not moving. That's why you get to absolute zero. That's the reason you have no negative temperatures. Because once the particles are not moving, that's it. You cannot cool the system down anymore. So by definition, this E average is just 1/2 m, the average velocity of the particles, VRMS square, and we find this nice expression here, and this basically encloses so much physics here. By equating these two expressions, and you can even, given the temperature now, You can know how fast the particles are moving. All you need to do if you find that if you want to know how fast the particles in the room that you're in are moving, just get the temperature and do this number here. And you should do this right now as an exercise. So, quick question here. A rigid container holds hydrogen, which is H2, and nitrogen, both at the same temperature. So remember, nitrogen would be way heavier than a hydrogen. Which one describes the average translational kinetic energy of the molecules better? The hydrogen is less than the nitrogen, they are equal, or the hydrogen is more than the nitrogen. Take a minute. And they would be equal, right? They would be equal because it only depends, E average is 3/2 kVt. It only depends on the temperature. That means that well, remember this is E average is equal to 1/2 n V RMS squared. So what this means basically is that the nitrogen is going to be moving slower than the hydrogen at this temperature. But they are both going to have the same average kinetic energy. And this is the main point of this video, the macro connections. And in this world here, in the macro world, we have pressure, temperature, volume, these macro quantities that we measure. Here we have, well, we have V, RMS, and we have the speed of the particles, and we have average kinetic energy, and we connect them. We connect them how? We use this equation here and this equation here to connect these two worlds. All right.